lecture, the first lecture in the second part of calculus, which is integration. In this lecture, we are going to give an introduction about integration. We introduce the two types of integration and start with the first type and describe the basic tools that can be used to solve the main problem in this type. So we start by classifying the integration problem into two types. The first type, which is usually called indefinite integration, is simply the inverse operation of differentiation, while the second part is called definite integration, is defined as a limit of the sum. So let's talk about the first type. The first type is called indefinite integration, and this simply is the opposite operation of differentiation. Is the inverse of differentiation. So we can, for example, say that we want to integrate. This is the symbol for this truth. We want to integrate this function. By integrating this function in definite integration, we mean to find another function whose derivative equals this given function. You can check that this answer is correct. How? By differentiating this function. If you differentiate this function, the result is exactly this function, so this result is correct. So this is the meaning of the first type of integration. Indefinite integration is simply the differentiation operation. For example, if the function represents displacement, differentiation gives velocity. If now we integrate the velocity function, the result is again the displacement function. Now, the second type is called definite integration. Actually, this represents a limit of a sum. Technically, it is a limit of a certain form of summation, which will be defined later on. But for the time being, this type of integration is the limit of a sum. Technically, it is the limit of Riemann sum. By limit of a sum, we mean that we have some function over some interval from A up to B, and we now go to this interval and divide the interval from A to B into small intervals of length delta x. Each subinterval, small subinterval, has a length delta x. And now we evaluate the function at some point inside these small subinterval, and then multiply f of xi, where f of x1 is the first evaluation in the first subinterval, f of x2 is the second evaluation at some point in second interval, and then multiply this f of xi with delta x, and then make a summation from I up to the last subinterval. I, say for example, from I equal 1 up to n, and then take the limit. Then take the limit as n, which is the number of subinterval, small subinterval approaching. This actually, by definition, is what's called definite integration. Definite integration. And the symbol is written as follows. It is the integration of the function f of x with respect to the variable x over the interval from A up to B. Again, the integration of f of x from A up to B is given by dividing the interval into small interval, evaluate the function at some point inside each interval, and then multiply the result with delta x, and then make a summation and take the limit and the number of sub-interval approaches infinity. This has many applications. One of the most famous applications is computing the area under some graph of this. Because if we wanted to compute this area, we want to have a specific geometrical formula that gives this result exactly. So what can we do? We can divide this interval into, for example, 4 subintervals, and then take here a rectangle to represent the approximation area of this rectangle, and approximation of the area under the curve in this subinterval, and then take another rectangle, and then take another rectangle, and a fourth one. Now the sum of these areas is an approximation. Is an approximation of the required area, but it is still approximation. If we increase the number of subinterval, we have a better approximation. Increase better and better approximation. How to get the exact result? By considering the limit, by investigating what happened to this summation as the number of rectangles approaching infinity. this case, we approach the exact. So one of the most important applications of definite integration, and that it represents what is the meaning of definite integration, is to compute the area under thumb. So again, definite integration, which is the second type of integration, is by definition limit of a Riemann. The two types of integration are connected by what's called fundamental theorem of integral, which simply speaking say, if you want to integrate this function, definite integration from sum A to sum B, simply you don't need to consider the limit. By definition, it is the limit. Its meaning is given by limit, but for calculation, you don't have to consider calculating the limit, but instead use this theorem, which says that you can evaluate this definite integration by finding first the indefinite integration of this function, which is this, and then substitute by the upper limit and the lower limit and take the difference. This gives the value of this definite integration, which represents the area under the function, which equals the limit of the sum of the rectangle areas and the number of rectangle approaches. So to summarize, we have two types of integration. The first type is the opposite of differentiation. The second type is the limit of a sum, and the two types are connected by what's called fundamental theorem of calculus, which gives a way to calculate different integration simply by relating it to indefinite integration. In our course in Math 1, we are going to consider indefinite integration first and give some basics about how to evaluate this, how to solve this problem, how to find the indefinite integration of some given function, and then also consider introduction to definite integration and see how to solve this problem and give some simple application. And both have some continuity in Math 1 chapter. In our discussion about indefinite integration, we are going to talk about first basics, which consider what is antiderivative and what is the relation between antiderivative and indefinite. This indefinite, not indefinite. And also we are going to consider what is called integration table, similar to differentiation table, and then consider integration rules. Actually, in this recorded lecture, we are going to consider this point, and start with both. So, integration rules. Actually, are going to consider three rules in this report. We are going to consider the first, and inshallah, in the second report, we are going to consider second and third. Now, let's start with antiderivative. Antiderivative, as the name suggests, is the opposite of derivative. So, if we differentiate x squared, the result, the derivative is 2x. So now we say the antiderivative of 2x equals x squared. And similarly, if we differentiate in x, the derivative is 1 over x. We say the derivative of ln x equals 1 over x. So we now say that the antiderivative of 1 over x is ln. And you can say similar statement to any entry in the differentiation table. For example, the antiderivative of 6 squared is tan x. The antiderivative of e power x is e power. The antiderivative of negative cosec square x is cotangent x, and so on. The antiderivative represents the basic part of the result. But actually, you can say that the antiderivative of 2x is x squared. Why? Because the derivative of x squared is x. But also the derivative of x squared plus 1 is 2x. X squared plus 2 is 2x. The derivative of x squared plus any constant is 2x. So we can say that the antiderivative of 2x, the general antiderivative of 2x, is x squared plus c. X squared plus c. And similarly for any other antiderivative. For example, the general antiderivative of 1 over x is ln x plus c. So ln x is the basic antiderivative. It is unique. But the general antiderivative is this unique antiderivative plus some constant c. So now the indefinite integration. Integration is the process and the integral is the result. Integration is the process and the integral is the result. As in differentiation. Differentiation is the process and derivative is the result. So what is indefinite integral? Simply speaking, the indefinite integral is the general antiderivative. The general antiderivative of something. And you write it as follows. Integration of f of x with respect to x by writing this equal f of x plus c. The result is correct because f capital, the derivative of f capital equal f. This is the check that the result is correct. Now, this symbol is the integral sign. This function, which is the function to be integrated, is called the integral. And this is the integration. This formula means that the derivative of fx equal f of small of x. So the antiderivative of x, which is the integration of x, equal f capital X. For example, the integration of 2x equal x squared plus c. Why? Because the derivative of 5 equal this. Now, we can simply, by this simple definition, simple relation between integration and differentiation, we can simply solve this problem by actually reversing the differentiation table. So what is the result of integrating cosine x? We can solve this problem orally. What is the integration of cosine x? It's sine x, because derivative of sine x equal cosine x. What is the integration of sec x tan x? It is sec x, because the derivative of sec x equals sec x tan x. What is the integration of 1 over 1 plus x squared? And this expression and similar expression appear repeatedly in integration problem. Integration involving result containing inverse function. Used frequently in integration problem. Result given in terms of inverse function, either in inverse trig function or inverse hyperbolic function. So now, what is the antiderivative of this function? Antiderivative is tan inverse, because the derivative of tan inverse equals this expression. So the result is directly tan inverse x. What is the derivative of 4x power 3? It is x power 4, because the derivative of x power 4 is 4x power 3 and so on. But now, if you are asking what is the integration of sec x, here we have a problem, because we don't have a function whose derivative equals sec x. We have to find combination of some function or some composite function whose differentiation equals sec x, because we don't have directly in the differentiation table a function fx whose derivative f dash of x or prime of x equal sec x. So we have to add this to what is called integration. So the integration table is basically the opposite of the differentiation, but we have to add some integral like integration of sec x. Before going into what is integration table and how to solve the problem in general, let's give some practical example to explain that integration, indefinite integration, is simply the antiderivative. For example, we assume that we have a ball which is thrown upward with this initial speed, and it was thrown starting from the edge of this cube, 130 meters above the cube. So this ball is thrown, it reaches some maximum height and then drop down. The first question is find its height as a function of time. Second question, when does it reach its maximum height? After how many seconds? And also, after how many seconds it hit the ground? Now, as this ball is thrown upward, we can say that its acceleration is given by this value. Now we can find its velocity, because the derivative of the velocity is the acceleration. So now the integration of the acceleration is the velocity. So we can integrate this function. Find indefinite integration. Indefinite integration of this constant. Simply speaking, the integration of any constant is the constant multiplied by x, or t is this thing, because the derivative of cx equals c. So in general, the integration of any constant is the constant multiplied by x, or the variable t. So this is the velocity. But the integration is in general the general antiderivative. So we have to add c here. What is the value of C? We can determine the value of C by applying the initial condition. We know the initial velocity. V of 0 equal 15. Is the initial V of 0 equal 15. So now if you substitute T equal 0, you find that T equal 15, and so you have a complete expression of the velocity. Now we can repeat the process to find the height function by integration this function. So give the displacement of the height function. We integrate this T, the integration will be T squared over 2, as we are going to see it. But you can check the space is correct by differentiating. Now the derivative of 15 will be 15t plus some constant c. How to find d? Again by applying the initial condition. Here we assume that the initial height is 130. We assume that this ground is the reference line. This ground is the reference line. Is the reference plane. So initially we have initial height, which is 100. So S of 0 equal 130. If you have substitute here and put D equal 0, you get D equal 130. So this is the function that gives the height of the ball after this. Now, the second question is about after how many seconds this ball reaches its maximum. When the ball reaches its maximum height, its velocity equal 0. Velocity equal 0. So we put V equal 0 and solve for it. You find simply that V equals this. Final question is about after how many seconds, the ball hits the ground. When the ball hits the ground, it hits the reference line, the reference plane. So at this point, the displacement equals 0. So the question is about when S equals 0. So we put this function equals 0 and solve it. Actually, when you solve for this t, you get two values. One of them is positive and the other is negative. So we reject the negative. We are talking about time and accept the positive, which is the number of seconds after which the ball hits the ground. So now we turn our attention to how to solve the problem of indefinite integration. How to integrate some given function. Actually, to integrate some given function, we have first to know what is the integration. Simply speaking, the integration table is the opposite of differentiation, but we write it in a form, simple form that facilitates solving the integration. We say that the integration of x power n is x power n plus 1 over n plus 1. We increase the power by 1 and divide by the new power. And you can check that this result is correct by differentiating to get x power. This rule is valid for any n, any real value n, except n equal negative 1, because in this case we are dividing by 0. What happens if n equal negative 1? This expression will be 1 over x. And we know the expression, the function whose derivative equal 1. It is len modulus. It is len x actually, but we write it as len modulus x. If we write it as len modulus x in order to get a function whose domain is equal to the domain of 1 over x, because len x only has a domain which is r positive, but this function which is 1 over x has a domain which is r minus 0, both of the negative respectively. But len x without modulus has a domain which is positive number, so we write it as len modulus. And you can check that the derivative of len x equal len modulus x equal 1 over x by writing len x, len modulus x as len x when x is positive. When x is positive. When x is negative, then len modulus x is equal to len negative x. This is for negative x. Now, if you want to find, this is positive x, x greater than, and this is negative x, x smaller than. Now, to find the derivative now, d by dx, d by dx. For the first part, the derivative of len x equal 1 over x. This is for positive x. Now, for negative x, we differentiate len negative x, which is 1 over negative x, multiplied by the derivative of negative x, which is negative 1. So now the result is again 1 over x. So the derivative for ln modulus x is exactly 1 over x. Now the integration of e bar x equal e bar x, integration of a bar x for any exponential function equals the same exponential function divided by ln x. We can apply this part of the integration table to solve such a problem. For example, x bar 3, the integration is x bar 4 over 4. Integration of root x, we can write this as x bar half. Now increase the power by 1 to be x bar 3 over 2 and divide by the new part. 3 bar x is an exponential function. You can apply this. The result will be 3 bar x over length. Now, this is the second part of the integration table, which is very important, integration of trigonometric functions. The first two entries are very simple. Integration of sine equal negative cosine. We put negative here. And you can check by differentiating this to get sine. The integration of cosine x equals sine x, because the derivative of sine x equals cosine. The integration of tan x equal length x, and we can write it as negative length cosine x. Negative length cosine. This is the same. Negative length cosine. And you can check that this result is correct by differentiating the right hand. The integration of cotan x equal length sine. The integration of sec x, which appeared before the problem. Integration of sec x equal length sec x plus tau. Integration of cosec x length cosec minus. We have to memorize this integration of the basic fixed function. Third part of the integration table, which is very important. Integration of some expression that yield inverse function, either inverse trig function or inverse hyperbolic function. These six inverse functions are the basic functions that frequently appear in integration problems. This one gives some inverse, this one gives tan inverse, this one gives sec inverse. These give sine inverse, which is similar to sine inverse. These give tangent inverse, which is similar to tan x, and these give cosine inverse, which is similar to sine inverse, but reversed in sign. So we can solve this problem directly by applying this entries from the integration. These give directly sine inverse. We have to memorize this. And this gives directly tangent inverse. And now, this can give tan inverse, but we have an additional 4 here. We are going to say that we can take 4 out the integral, as we are going to explain now. So this will be 4 tan inverse. Now, x squared over 1 plus this is the problem. How to deal with this? It seems that it is similar to this, but we have x squared. We cannot take x squared outside the integration. We can take 4 because it is a constant. X is a variable. We cannot take x or x squared outside the integration. So we have to have some rules in order to solve such a problem. So we are going now to talk about integration rules. As I said in the introduction, actually we are going to consider in Math 1 3 integration rules. In this report, we are going to consider the first one of them. And in the second report, we are going to consider second and third rule. This first rule is usually called linearity property, which is similar to similar property in differentiation. If you want to integrate k multiplied by some function f, you can take k outside the integration. So it will be k multiplied by the integration. And if you want to integrate sum of two functions, the result is the sum of the integral. And the same for subtract. So this simple rule is very important, and we can solve many problems. Actually, in order to solve problems using this rule and the other rules, always we have to make some manipulation, usually some algebraic manipulation, or use some trigonometric identity in order to put the given problem in the form of this rule or other rule. So integration problems in general need practice in order to know such things, how to convert the problem to be similar to the form of some of the given rules. You have to practice a lot in order to get experience in dealing with integration problem. Integration problem is tricky in nature, not similar to differentiation. Differentiation is systematic, but integration is tricky. So let's start with this. How to deal with it? We can say that we can distribute the numerator over the denominator and say it is 2x power 3 over root x plus 4 over root. Now, after making this, we can use now this property in order to divide this integral, this problem, into two sub-problems and deal with each separately. And it's expected to be that each sub-problem is simpler than the original problem. So now this problem can be integrated simply by increasing the power of the by 1 and dividing by the new power, and also this. It will be x power negative half. You can increase the power and divide by the new. Consider another example. If you have this expression, how to deal with it? We can say that we increase the power and divide by the new power. This happen only for x raised from power. But now we have some bracket. Can we say that we can, for example, make something like the chain rule? No, we don't have something like that. So how to deal with it? We can simply expand this bracket. Expand this bracket. And then integrate, because now we have three terms. We can integrate each term separately. This simple trick. Expand the expression and then apply the numerator property and integrate each term information separately. Consider, for example, this x squared over 1 plus x. Here we cannot distribute the numerator over the denominator because the summation is in the denominator. We can make such distribution only when the summation is in the numerator. So how to deal with this? We have a simple trick. We can add 1 and subtract 1. And now we can consider x squared plus 1 and negative 1 in the numerator to be distributed over the denominator. So this bracket over this bracket gets, and this bracket, this one will be over this. And now we can integrate these two expressions. The integration of 1 is x. The integration of this expression is tan inverse. Again, tan inverse and related functions, sin inverse, related, appear repeatedly in integration. Consider this example. You can apply a similar idea. Add 1 and subtract. But in this case, and you need to continue to yourself, if you separate the numerator into two expressions, 1 over this expression will be exactly as this one. But x power 4 minus 1 over x squared plus 1 is different somehow. So in this case, you have to make a factorization of this expression into x squared minus 1 multiplied by x squared plus 1, and then there is another idea which I am going to explain now. In order to deal with this expression, we can simplify it first by applying long division. Let's consider this process. We now want to divide x power 4 by x squared plus 1. What we're going to do, we start by dividing this term, the first term in the numerator, which is the unique term in the numerator, by the first term in the denominator. The result will be x power 2. Now we multiply x power 2 by this expression. This gives x power 4 plus x power 2. And now make the subtraction. X power 4 minus x power 4 is 0. 0 minus x squared equal negative x squared. We repeat the process again. Negative x squared over x squared gives negative 1. Multiply negative 1 by this expression. Give negative x squared minus 1. Now make the subtraction. So this will be 0 and this will be positive 1. The division is complete now because this expression is of degree 0, is a constant. And this is degree 2. This degree is smaller than this degree. So the division is complete. But here, the division is not yet complete because we have an expression of degree 2 divided by another expression. So you stop the division when the result of the degree is smaller than the expression in the numerator. Now, what is the result? Division in general has a quotient and the remainder. For example, if we divide 7 by 2, The result is 3 and half. 3 is the result, the quotient, the integral part of the result. That is the quotient. And now you have also 1 divided by 2. This one is the remainder. 1 is the remainder. We have a similar shape. The quotient is x squared minus 1, and the remainder is 1, which is divided by x squared plus 1. After making this long division, the integration problem will be very simple. Integration x squared, x power 3 over 3, integration of 1 equal x, and integration of this expression equal tan inverse. So this idea is very important in order to simplify this rational function, in order to make it amenable for integration. Using trigonometric identities is frequently used in integration, and you have to be familiar with using such identities. Let's consider some example. We want to integrate tan squared x. We don't have an entry in the integration table equal tan squared. How to deal with it? We can use the trigonometric identity, which says that 1 plus tan squared equals 6 squared. So we can say that tan squared equals 6 squared minus 1. What is the benefit of this? The benefit is that integration of 6 squared is known. It is tan x, because derivative of tan equals 6. So tan squared, we don't know what is the integration of tan. So we convert it into 6 squared, because we know the integration of 6. Integration of 1 equals phi multiplied by cosine. This of course appear in the rule of sine 2x. So this will be half sine double angle. So it will be half sine 2 multiplied by x, which is sine x is very simple. Consider sine square x over 2, which is very important. Now, the solution of this problem uses the basic rule of cosine 2x. The basic form of expanding 2x is cosine square x minus sine square. But now we can write this right hand side in terms of sine only or cosine only. If we replace cosine square by 1 minus sine square, we get 1 minus sine square minus sine square. So we have 1 minus 2 sine square. Now if we break sine square in a side, we get sine square x equal half 1 minus cosine. 1 minus cosine 2x. And this will be used in this problem. So we can replace this sine square, because the problem here is with square, how to deal with this square. We don't have a rule to how to integrate sine square, since we have the integration of sine. How to integrate sine square? We don't have a general rule for the product, how to integrate the product of two functions. Integration don't have such having differentiation. So integration problem in general is tricky. We don't have a rule to integrate product of quotient or composite function in general. But in this case, if we use this rule, we can write result as integration of 1 minus cosine 2 multiplied by, here we have x over 2. So we have 2 multiplied by x over 2. So it will be cosine. This expression is amenable for integration. This will be x and this will be a sine. So using this rule is very important integration topic. And this rule have another similar one, which is that cosine square equal half 1 plus cosine 2. Half 1 plus cosine 2. So these two rules are very important. This rule is also derived from this rule. You can say that cosine 2x now equal, by replacing sine square with 1 minus cosine square, it will be 2 cosine square minus 1. And if you break cosine square on one side, it will give half 1 plus cosine. So these two rules are very important and are used frequently in integration in order to replace a function sine or cosine raised to power 2 to a function without this power, which is very important to solve the integration. Another idea, 1 over 1 plus sine x. The problem here is that we have a summation in the denominator. We cannot now make a distribution in order to break the problem into two subproblems. Problem which is expected to be simple. How to deal with this? The idea here is that we can multiply by the conjugate, which is 1 minus sine. 1 plus sine multiplied by 1 minus sine gives 1 minus sine square, which is cosine square. And this is very good because now we don't have summation in the denominator. And summation now will be in the numerator, which we can use to simplify the problem by distributing the numerator over the denominator. 1 over cosine square is 6 square. Sine over cosine square, which will be tan multiplied sine over cosine, which is tan. 1 over cosine, which is 10. Now, these two functions have known integrals. The integration of 6 square equal tan. Integration of tan multiplied by 6 equal. So this is another important idea by multiplying both numerator and denominator by the conjugate. And the motivation for this is to give rise from this plus sign and to convert it to the numerator in order to be able to break the integration into two simple subgroups. Actually, you can check additional example in your text in these 2 pages in order to make a lot of practice on integration problem, because again, integration problem is tricky and you have to make a lot of exercise in order to get experience solving such. That's all for this introduction about integration. And again, as we said in the introduction and during the lecture, that integration rule, we are going to consider 3 rules. We consider this before the first rule, and in the second report, we are going to consider the second and third. Thank you.